Here is Ben Gwilliam's going to talk a little bit about LiDAR. Take it away, Ben.
Okay, so I'm going to be talking today about approaches to modeling change in forest inventory attributes from an outdated 2014 LiDAR dataset. So this past year, the Ontario Woodlot Association spearheaded a private lands forest inventory project based on LiDAR information for an area in southeastern Ontario. However, this LiDAR data was from 2014. So as part of that project, a research question was posed: how can we model a change or grow the forest inventory forward for present-day analysis? I was given the task of finding a way to develop adjustment factors for the LiDAR estimates of FRI attributes generated from the 2014 LiDAR dataset, things like basal area, volume, height, etc. My objective and the focus of this presentation was to develop a protocol for collecting new calibration data, go back and collect that data, and to model the change in FRI attributes through an exploration of linear regression and random forest methods. I would then determine which was the most suitable model to apply across the landscape covered by the LiDAR inventory. I want to start by briefly describing to you aerial LiDAR. So a laser scanner with a built-in sensor is typically flown from a plane or drone. The laser is emitted and then bounces back and received by the sensor on the plane. The GPS information from the plane means the exact point in space where that beam was returned is known. One beam can return multiple times, and each return sends information on the location of where it was intercepted. From this, we can determine an accurate picture of vegetation structure. All of these returns exist as points in space, or a point cloud. And as we zoom out, a picture emerges. And from this, we can see and measure features on the landscape in 3 dimensions. This is from the LiDAR data used for the project and is color-coded to represent height. From the point cloud is also generated descriptive statistics, 114 in total, representing returns from a 20 by 20 meter area. As you can see, most describe different levels of height and density and are thus highly correlated to each other. When used as variables to predict inventory attributes, the collinearity poses a significant challenge for linear models. This makes machine learning, like random forest, the preferred method for predicting FRI attributes from these statistics, as it is more robust to collinear variables. And random forest is what is being used in producing the provincial FRIs based on LiDAR. And so because random forest is used in producing inventories, it formed the justification for this study to use it again to try and predict the change in these attributes. This image illustrates what one of the 114 LiDAR statistics looks like in a spatial context. Each 20 by 20 meter raster cell corresponds to a generated statistic cell, so in total, 114 different rasters can be generated from the raw point cloud. This raster also illustrates that I've masked the LiDAR data to only reflect the forest portions of the study area. So I want to first take you back to 2014 and describe how the inventory was initially modeled. This red line, you can kind of see it, delineates the area of United Counties of Prescott and Russell, an area of the private land inventory developed by the OWA. It is about 2,000 square kilometers and just east of Ottawa. Here you can see LaRose Forest, where the 2014 LiDAR data was calibrated and the 2021 data was gathered. LaRose Forest is representative of the forest found in the region and provides a good sample location. This county is within the Great Lakes St. Lawrence Forest region, and for a fun fact, this area hosts the southernmost moose population in Ontario. Generating the 2014 inventory was done using the area-based approach, which utilizes ground plots to calibrate the LiDAR point cloud, 200 plots of which were established in LaRose Forest across a range of forest conditions. Each ground plot was measured for location with high accuracy GPS, and all trees were measured for height, diameter, and condition, and thus the basal area and volume. This allows for these structural measurements on the ground to be correlated with the point cloud at the same location and aggregated to the stand level. Again, this is where random forest is used to predict these attributes, height, basal area, volume, etc., for the area not sampled, based on the known attributes of the 200 plots and the relationship to the point cloud. And here we have the final LiDAR inventory products. The 3 critical to my capstone are the predicted average height, basal area, and merchantable volume. But of course, other FRI attributes are also predicted from LiDAR, examples you can see below. All right, so fast forward to the present day and the methodology I used for modeling the change in these attributes since 2014. First, we returned to LaRose Forest in Prescott and Russell to collect new data. I developed a protocol to intensively cruise a sample of stands representative of the greater landscape. With the final sample size of 31, you can see that both forest type and basal area were considered. This was particularly challenging to design due to a number of constraints. For example, I could not choose from stands which had been harvested or experienced significant change since 2014. The stands had to be reasonably accessible, and where possible, the stands should be within the Rose Forest 5-year operations plan, so they may also make use of that information. So you get an idea of the scope of the sampling effort. This is a map of the stands that ended up being sampled in the Rose. Roughly, you're looking at an area of about 150 square kilometers. At each stand, variable radius plots were established with all trees live or dead above 9 centimeters DBH measured, along with the heights across a range of size classes. In total, about 28 of us measured over 2,600 trees in less than 24 hours. Here you can see how the plots were laid out. I used a 50-meter fishnet grid with a buffer around the stand edges and roads, and used a random number generator to select each plot. I went with about 1 plot per hectare natural stands and 1 per 5 hectares in conifer plantations. First, I'm going to begin by talking about the regression approach to modeling the change since 2014. I first verified the assumptions for parametric tests. I then calculated the annual increment from each stand for each attribute by subtracting the 2014 data from the 2021 data and dividing by the time elapsed. I then used a polynomial or quadratic regression approach model, to predict annual increment using the trendline formula. This prediction of annual increment was then applied to the 2014 LiDAR data after multiplying by the number of years that had elapsed. As you can see here, the homogeneity and variance of the residuals, the distribution of the residuals, while not great, are not bad either. So this gave me confidence to move forward with the regression approach. Here you can see the basal area regression model. I fit the line intercept at 0 because with 0 basal area, it's assumed you would get 0 increment. On the x-axis are the 2014 LiDAR values, and the y-axis are the annual increment calculated from the 2 data sets. The quadratic formula for the trend line used to make the predictions is in the top corner, and you'll see that it is statistically significant with a decent R-square and p-value. You'll also see on the plot that to the right is mostly conifer plantations, while the left are hardwoods, and this reflects their presence in the landscape, as there were no available low BA plantation stands, and the high BA hardwood stands had already been harvested. This is primarily the reason, along with a small sample size, that I decided to go with an all-forest type model. Otherwise, when not combined, the data lacked a normal distribution. You'll also notice that some stands showed a negative increment in basal area, which I can hypothesize could be from natural senescence or disturbance, or is an artifact from sampling technique. Similarly, here's the volume model with volume increment plotted against the 2014 LiDAR data. Again, plantations are taking up the higher volume areas, with some stands experiencing a decrease in volume. Regardless, this decrease reflects natural conditions, as it's not expected that all stands would show growth in increment due to the factors I mentioned earlier. This had the poorest R2, but R-square, but the relationship is still determined to be statistically significant. And finally, here's the average height regression model. You'll see this one has the highest R-square of all the models, and the relationship is very statistically significant. Before moving on to the random forest approach, I want to briefly describe roughly what is happening. So random forest is a machine learning algorithm that at its heart is a group of decision trees. This example is with predicting basal area increment. It is first fed training data, which are known measurements, in this case, the calculated BA increments in the original FRI, in the original FRI, it would have been the ground plot data. Then it creates a random set of associated variables, in this case, the LiDAR statistics that I showed earlier. At each node of the tree, it is determining correlation between these variables in a measured increment and picking the best ones, which go on to pool with another set of predictors at a subsequent node. Eventually, all of the trees created from the random subsets of the training data are combined and their predictions averaged to form a model. This is why it is robust to collinearity, as it's always sampling and resampling a different set of variables each time. It is an excellent technique when underlying distributions are unknown and parametric approaches are not possible. However, with random forest, it is generally a black box, and the LiDAR statistics it used at each node to make a prediction may not even make ecological sense. It also does not produce trend lines. This means that random forest can only predict from within the range of data that is given and cannot extrapolate beyond that range. So it requires large representative sample sizes for precise predictions. In my study, for each increment observation, random forests use 1,000 different trees with a set of 30 random LiDAR predictor variables at each node. This outlines how I use the random forest approach to predict the annual increments for each inventory attribute and is similar to how I applied the regression results. I use the calculated increments known from the 2014 and 2021 data as training data to feed the model. I then applied the random forest predicted annual increment in the same way as in the regression model. And here are the results. RMSE, or root mean squared error, is primarily how I'm comparing the predicting ability of each model. It considers the residuals from each model, or the difference between the predicted value and the observed value, and quantifies that error, so a lower RMSE value is better. RMSE is great because it gives a higher weight to larger errors, and output is in the same units that are being measured. The left bar is the RMSE for regression, and the right is for random forest. You can see here that based on RMSE, random forest very slightly outperforms regression on each of the attributes, but the results are not the whole picture. And so while random forest did outperform regression, I chose to go with a regression model. And I'm first going to show you the results from that model applied to the landscape. I chose basal area and height for the sake of time for this presentation, two important measures for management decision-making, and also from which you can derive volume. I'll then explain my justification for choosing regression. First, here's the raster for BA for Prescott and Russell from 2014. That's the range of values on the right. And here is the BA regression predictions for the landscape in 2021. Pay attention to change in those mid-range values, the yellows and greens. Subtle, but you can see it. But here you can see the histograms generated from the rasters, the rightward shift in basal areas and the decrease in extreme high basal areas from 2014 due to that quadratic curve. But you can see that the average BA is increasing overall. However, what is not captured in this modeling are the establishment of new stands being recruited into the lower size classes. And here is the average height in 2014. And this is the regression modeled average height. So you can see a change mostly in those mid-range values, the green and yellow, which match the apex of that quadratic curve, which would experience the highest increments in growth. And again, here's the increment, see again here with average height, the heights of the apex of the quadratic curve are shifting right or growing. And we're seeing less extreme growth at the high end. And at the low end, you're seeing that issue again with a lack of recruitment into the smaller height classes. So yes, random forest is a powerful tool in most contexts, but not here. It has difficulties extrapolating from the narrow range in training data. As you can see, the training data, which are the numbers on the left, do not cover the range of variation in the landscape and the numbers on the right. This would lead to wildly inaccurate predictions for random forest for any values in the 2014 data that are outside this range on both the low and high end. But with regression, the trend line can be used to generalize beyond the data set it was built from. But also why quadratic regression in particular works so well is that the parabola matches biological expectations of the change in stand growth increments as it does with other population density type curves. For instance, the curves used to determine optimal harvest show how a stand reaches a maximum growth rate at a certain age and begins to diminish, just like how the quadratic trend line I used models the maximum growth at their optimal basal areas, volumes, and heights for additional growth. So what I found was that it is indeed possible to model change from an outdated LiDAR data set. And with this study, we have an established methodology with significant results that seem reasonable when applied to the landscape. This is especially useful in a private land context in Southern Ontario where frequent up-to-date LiDAR data and growth and yield models may not be available. The OWA hopes this application can be used for decision-making and developing a present-day inventory for the south of the province, which hasn't been done since 1978. Future studies should focus on larger sample sizes with improved species resolutions and age that would allow for precise species-specific modeling. And most importantly, it is important to consider that this modeling is on top of already modeled data. And what isn't being modeled is the change in land use, forest loss, establishment, and species succession. And for that, we'll just need to fly new LiDAR. Thank you. I'd just like to do my acknowledgements quick. This is from Murray Woods. You're an inspiration that fostered in me a passion for resource management, LiDAR inventory, which I'll carry with me throughout my entire career. John Pinot and Paul Robertson, Executive Director and President of the OWA. I'll always be grateful for my experience and proud to be a member of the OWA. Al Stinson, Pete Arbor, and his Algonquin Forest students, and of course, their very own Sean, who helped me in their monumental effort in collecting the data this past August. My supervisor, Professor Kuttner, for all your thoughtful feedback, advice, patience, and understanding. Professor Malcolm for turning me on to random forest in the first place and your excellent statistics instruction. Steve Hunter, the Forester at La Rose, for being a gracious host, and my fellow MFCs, you guys rock. Thank you.
Thank you. Thank you very much, Ben. I'm going to pass the mic to another Ben for the initial questions.
All right. Good job, Ben. As you know, this is a very large undertaking, doing these kind of LiDAR analyses, just given the volume of the data and the skills you developed using R and figuring this all out is really laudable. So I have a question, and that is, what do you think would result in a bigger improvement in your models if you were to sample stands, like instead of 1 plot per hectare at 2 or 3, or if you were to sample more stands?
Well, if I were to sample more stands that have a greater range of data, I believe I'd get more precise models from that. More stands would also mean I could split the modeling into at least plantation or hardwood models, which would obviously demonstrate much different growth increments. So more data overall would definitely improve the precision of the results, but I think 1 plot per hectare is about standard for a cruise, and I'm unsure if any more than that would really be necessary within the stand, but more stands would certainly be beneficial. As far as coniferous plantations go, you wouldn't need more than 1 plot per hectare because there is not a lot of variability within stands like that.
Mm-hmm. All right. I would tend to agree, actually.
It's also limited, like resources available, right? Yeah.
Now, have you ever given any thought to how you might go about improving the species detection with LiDAR, or thought about working this in combination with any kinds of imagery, as we've seen from Jay's work?
Absolutely. That's been attempted on the landscape. The results are very poor just because of there's just so much species mixture happening. There's not very good ground plot calibration data for that region. Right now, Solris, I couldn't get results that were better than Solris. So Solris is being used for species. This is for the subsequent economic analysis being done using this data, is using Solris to determine the species, or at least the forest type, not really species, the forest type. But it's hard to say if an improvement in methods would work. It's just, what's out there on the landscape is such a huge mixture, rather than you get the pure stands of black spruce, you get the pure stands of pine and conifers that you'd see up north. It's not really present down here as much. It's very fragmented, small stands.
All right. I'd like to know if anybody else has any questions.
I think John has a question, and I've got a question. If there's else.
Oh, should I go first? Okay.
Yeah, please go
You
ahead.
certainly can.
Okay. Good job, Ben. Very interesting. You were very careful to say that extrapolating beyond the range of stand structures using the random forest method would be problematic. But you didn't really address that with respect to the regression. And I wonder if there isn't some concern there that, for example, your fits go through 0 at 0 basal area. For example, I'm just wondering if there isn't some extrapolation issues with the regression method as well. So in particular, question I have is, did you fit quadratic functions, but did you test them against, say, other maybe just linear functions to see if they were actually statistically significantly better than something that would be simpler, although perhaps biologically unreasonable? Because it seemed like there was a lot of, your data set was quite variable. So I guess just to reiterate my question is, did you say compare the fit of quadratic functions to, say, linear functions or alternative functional forms?
I didn't do an initial just straight linear modeling, just because it was supposed that you wouldn't see that kind of growth, like continuous linear growth in nature. But with the quadratic functions, and you're right that at the extreme ends on both sides, you could see negative growth. Luckily, on the landscape, those types of stands, which going beyond, say, 40, 50 BA are not, there's not many of them. So I think the effect would likely be minimal. You see the majority of the stands are within the 15 to 25 BA range. So that it's understandable that, yes, at the high BA range with the quadratic function, you're going to see probably worse results. The same with the low end, just because of the function of that curve. But no, just a straight linear model was not attempted, just due to the thought that there wouldn't be continuous growth. The idea is,
Okay, thanks.
yeah.
I think there was someone else online with a question.
Yeah, hi, Ben. Well done, Jay here. I was a bit curious. I was a bit confused about the species part of it. I mean, from what I recall of your quadratic fits there, a lot of the variation was due to different stand types. And I would have thought, you would, do separate modeling for separate stand types, at least some crude representation of stands.
Right.
And I thought you had the FRI, so you've actually got pretty sophisticated representation of stands. So I was a bit confused, like, why did you incorporate the species mix into the modeling, or for this first cut, no?
So I tried to just I used the FRI for LaRose and their forest units, how they defined them. And I did do a spread of the forest types that are typically found in the United Counties of Prescott and Russell. Unfortunately, because the sample size was so small, I did try doing separate modeling for plantations and naturally established stands. And the data was not normally distributed. I couldn't do any kind of regression modeling with it. And the random forest results were very poor. So that's why I went with a mix of stands and stand types. And with the larger sample size, I definitely would have done maybe not a species specific model, but at least a hardwood coniferous model.
Yeah, I get it now. You're right. I mean, you're constrained fundamentally by those sample sizes there. Yeah, you're right.
Right. But these are the stand types that were present. These were also the stand types that showed the best response to the initial LiDAR modeling. So these were the ones that had the strongest results from the initial modeling.
Cool, thanks.
I just had a quick question for you, Ben.
Yeah.
Awesome job. You mentioned that you randomly selected your plots for 2021. I'm just wondering why you didn't reuse the 2014 plots.
That's a good question. And undoubtedly, it would have led to better results because, like I said earlier, with you're modeling on top of modeling with this. So you have to use extremely accurate GPS for those initial plots, stuff that's measured in centimeters. Unfortunately, we didn't have access to that, that equipment. So instead we used Avenza maps, and they had their cell phones to kind of GPS coordinate them. So I would have loved to have been able to revisit those plots and do the same measurements again. And then that definitely would have tracked a much more accurate change.
So those stands didn't see too much change between then and now. You'd still be able to use them if you had the measuring equipment, like to get you there?
Absolutely, yeah. The location's known, and if this equipment takes, you literally have to stand there for hours to get a good signal to calibrate it. It's crazy, but you didn't have access to it. So thank you for the question.
Okay, thank you very much, Ben.